Shunbo is a research fellow of the University of Michigan, have a PhD degree in electrical engineering from the University of Hong Kong in 2017, and it was a visiting scholar of Argonne National Laboratory from between 2015 and 17. His research interests are power system operation, demand response, building energy efficiency, convex optimization, and machine learning. We'll play the video. Just 1 second.
Hello everyone, my name is Shunbo. I'm a postdoc with the University of Michigan. Today I'm going to talk about our paper using Tensor Completion to estimate the baseline of commercial building HVAC fan power. HVAC here means heating, ventilation, and air conditioning systems. My presentation today will flow like this. First, I will talk about the background and motivation of our work. Then, I will introduce our new baseline method based on Tensor Completion. After that, I will present the metrics, data, and the numerical results that we use to assess the performance of our method. Finally, I will provide the conclusion and propose some future research directions. So, baseline estimation is to predict what the power profile of a demand response participant would have been if the demand response event did not happen. In the literature, we already have many different kinds of baseline methods. The most common one might be the averaging methods, which are easy to implement but typically have large errors. There are also conventional regression methods typically based on outdoor temperature. These methods do not work for weather-insensitive loads, for example, the HVAC fan power load in this work. And we have control group methods and machine learning methods. They require very large data sets, which are not easy to obtain. And machine learning methods are very hard to interpret. And more importantly, these methods are developed based on whole building power profiles. So, due to all those reasons, those methods generally do not work in our application scenario, which is to baseline the short-term load shifting of HVAC system supply and return fans. We hope to do that because commercial buildings account for about 20% of energy consumed in the United States. And those buildings typically have large thermal inertia so that their HVAC systems can be controlled for demand response. And the primary response is from supply and return fans. Here, I provide two examples of research that modulate HVAC fans for demand response. In this reference, HVAC fan power is controlled to track a frequency regulation signal. And at the University of Michigan, we have been conducting experiments of shifting HVAC fan power load in sub-hourly timescales. As a result, we need a baseline method to achieve more accurate and more granular analysis of the HVAC fan power. Actually, the literature has two methods specifically for baselining HVAC fan power. This reference has proposed a signal bandwidth separation method. It assumes that the baseline fan power has a much lower bandwidth compared with the power change due to the demand response signal. And this method is only useful when the demand response signal is high frequency, which is not the case in our research. In those two references, a simple linear interpolation method is used. As shown in this plot, it used least squares to fit a linear baseline to fan power data 5 minutes before the demand response event and 5 minutes after the fans return to their baseline operation. However, the performance of this method is not consistent. So, we need a new baseline method. Here, let me introduce tensor decomposition first. In our application scenario, we arrange the fan power data into a three-dimensional tensor like this. Its dimension is the number of time steps every day times the number of fans times the number of days. For each day, we have a slice which contains the daily power profile of each fan. Note that our objective is to baseline the total fan power, but you will see that it's good to use per fan power data in our method. And what tensor decomposition can do here is to approximate the original fan power days tensor by the sum of a number of outer products. And each outer product here involves a time factor L, a fan factor omega, and a day factor omega with a bar. This rank R tensor decomposition can be obtained by minimizing a loss function that penalizes the differences between the entries in the original and approximated tensors. In general, tensor decomposition can be seen as an analog of PCA in a higher dimension, and it does not require the factors to be orthogonal. As a result, it can produce more interpretable results. And one important feature is that it can capture the correlation along different dimensions. In this earlier work, we have tested the capability of tensor decomposition to capture fan power patterns. In this figure, the first column are the fan power patterns obtained by tensor decomposition, and the second and third columns are the weights of power patterns in different fans and in different days. The first row is the most dominant fan power patterns, which is very similar to the common daily power profiles of HVAC fans. And this pattern is actually the fan power change due to our load shifting experiments. So based on these results, we believe that tensor decomposition works well in capturing fan power. As for tensor completion, in general, it's tensor decomposition with missing or unknown entries in the tensor. And that is, when computing this rank R tensor decomposition, we only consider the known entries in the loss function. By doing this, the known entries are approximated, while the missing entries are estimated, assuming that the missing entries follow the patterns of the known entries. So, in our application scenario, we assume that the fan power data within demand response windows on demand response days are missing. And we can use tensor completion to estimate their values, assuming that they follow the fan power patterns represented by the data we know. To solve this tensor completion problem, we use the limited memory BFGS algorithm with bound constraints. And since this is an non-convex optimization problem, we run the algorithm multiple times and choose the solution with the best objective value. We use three metrics to evaluate our baseline approach. The first one is CV, the coefficient of variation, and it's defined as the standard deviation of estimation errors normalized by the mean of the true values. And more accurate baselines have lower values of CV. The second metric is NMBE, the normalized mean bias error. It's defined as the mean bias errors normalized by the mean of the true values. The final one is called AEC, additional energy consumption. It's similar to NMBE, but without normalization. And it's used here to evaluate baseline errors when the baseline approach is used to estimate energy consumption. In our evaluation, we use 5 data sets corresponding to 5 different building years. The original data is in 1 minute resolution, we assume two demand response event windows, one in the morning from 9 to 11 and the other in the afternoon from 1 to 3. Note that we are using data from baseline days without demand response experiments, so that the measured power data during event windows is the true baseline. We conduct leave one out cross-validation for each building year. That is, each time we use Tensor Completion to estimate fan power baseline, we assume that just one day is a demand response day to be baseline. After doing that for every day, we summarize the statistics of the evaluation metrics. First, let's see how the temporal frequency of data impacts our Tensor Completion baseline approach. This table shows the mean values and standard deviation of the accuracy and bias metrics when different temporal frequencies of the data are used. And let's just focus on 1 billion year and only look at the afternoon event window. So, the HVAC recommends that when using hourly data, CV should be lower than 30%, and the normalized mean bias errors should be smaller than 10%. We are using sub-hourly data here, so the tolerance should be less strict. So in general, the performance is acceptable across different data frequencies. Still, somehow, the proposed approach generally has the best performance when using 15 minutes interval data. In this case, it attains the smallest CV in most cases and small normalized mean bias error in all cases. And when using 1 minute interval data, the proposed approach has the worst performance because it's hard to capture high frequency variation in 1 minute interval fan power data. Next, we fix the temporal frequency of data to be 15 minutes and try using total fan power data instead of per fan power data. When we use total fan power data, the tensor completion reduces to a problem similar to matrix completion. This figure shows the comparison. Let's focus on just 1 billion year. Here, the upper plot compares the accuracy, and the lower plot compares the bias. Different colors in the same plot correspond to different demand response windows. The error bars are standard deviations. As you can see, when using per fan power data, our approach has lower values of CV and NMBE. These results support the use of three-dimensional fan power data here, which allows the tensor approach to capture fan power patterns that are consistent among different fans and over different days. Here, we compare our baseline approach with three benchmarks. In this figure, baseline 1, BL1, is our tensor approach. And baseline 2 is the linear interpolation approach. Baseline 3 is the 5-day average method. And baseline 4 is the nearest 3 of 6 method. Again, let's only focus on 1 billion year. In this row, the first two plots compare the accuracy for the morning and afternoon event windows, and the last two plots compare the bias. As you can see, the tensor completion and the linear interpolation approaches are better than the other two, with the tensor approach generally the best. And here, we further compare the AEC bias of the tensor approach and linear interpolation approach. In this table, the smaller AEC bias in each row is bolded, and the upper and lower halves of the table are the comparisons for the morning and afternoon event windows respectively. In general, our tensor approach is better for the morning demand response window. Its performance for the afternoon event window is also comparable to the linear interpolation method. And the linear interpolation method is generally better for the afternoon demand response window. However, it has large bias in some cases, which means that its performance is not consistent. So the first conclusion is that our tensor completion baseline approach is promising. And the temporal and spatial resolution of the data have some impacts on our approach. And in the future, we will study the selection of rank in our tensor completion to better balance the trade-off between data overfit and approximation error. We are also going to study the adaptive selection of baseline approaches, since different baseline approaches can work well in different situations. And thanks for listening.
Okay, so
Thank you for playing.
okay, I think we don't have yet any question on the Q&A. So I can make the first question. So I will start by discussing that last slide where you mentioned the adaptive selection of the baselines. Have you considered some kind of ensemble of the baselines, so a combination of multiple models to improve it, the estimation?
You mean to have a model that adaptively choose the best performance in that scenario, or are you
or not trying to find the best one, because the idea of ensemble is to have a solution that is close to the best one and you don't know which one is the best. So I would say to have something that would be close to the best model for each situation.
Yeah, so as you can see, I have compared our proposed baseline approach with 3 benchmarks, and those 3 benchmarks were identified as the best 3 baseline approach for our application scenario in one of our reports. Yeah.
Okay. And another question, it's who will use this, will calculate this baseline? Is the aggregator to define the flexibility offer, or it's like DSO or a retailer to calculate how much they should bill in terms of electricity consumption?
I think the building owners, building operators, and also as you said, the aggregators will kind of may choose to use these baseline models to estimate how the fan power will change due to the demand response signal, and design their demand response incentives and their control strategy, and maybe also to see how much money they should compensate for the power change of the HVAC systems in commercial buildings. Thank you.
Okay, so I think we still have some 2 minutes, no questions, but I have questions. So another idea that could be interesting for you is to explore some probabilistic estimation of the baseline. For example, to have some confidence interval, and then they can select the best quantile for a specific problem, for example, to offer.
Yeah. So, I guess one idea is to test the baseline approach based on some baseline data, so that we can know the exact error among the when the baseline approach is used to those baseline data, and as you said, to calculate maybe some statistic values to represent the error or confidence interval for this baseline approach, and then use this confidence interval to see how good is the baseline approach when it is used to the non-baseline data. Yeah.
Okay, thank you very much. So I would like, so we are on time, so I'd like to end the session by expressing my gratitude for all the speakers. There were very high quality papers and presentations, and all of them managed to comply with the time, so we'll finish this session on time. So I'd like to thank everyone, for also the attenders for being here, and the speakers, and see you not on the coffee break, but on on the next session.
Thank
Bye.
you.